I ended last time over here about the cost function, and I want to go back up. The next step is, after evaluating the guess, is to figure out how to update our guess, right? And so we have this right here, which is basically, we can't see W in here directly, but if you look here closer, there's WX. In our example, that's what Y hat represents, right? And so in order to find out how to update the guess, um, I want to give you a graph real quick. So I want to visualize what J looks like as we vary the value of W. So J is the cost, or how badly our model is doing. And let's say there is an ideal value for W, which is right here. Maybe this is 0, let's say. And then this is W star. This is the best possible value for W. Um, and even at that value of W, let's say that there still is a positive cost, right? It's the best that it could possibly be, but it still doesn't go exactly through all of the points, and therefore there still is a mean squared error. Um, and let's say for 0, it was pretty bad. That was our initial guess, which was pretty bad, very high cost. And if you plot for different values, what ends up happening is you get something along the lines of this, like a parabola. If you know about what a parabola is, it's kind of like a parabola. And as you vary for different values of W, you'll get this sort of curve. And I just want to know that given a point here, let's say we started at 0, how should we know that we have to increase our value of W? Well, what would happen is that in order to get a lower cost, right? In order to get a lower cost, technically, based on this graph, right? If you were only given this graph and you were asked to find out based on the value of 0, should I increase or decrease the value of W? You would say increase, right? Because as we shift from 0 to the right, we slowly start to decrease in value for the cost function. And therefore, that means that our model is doing better. Our line is kind of going closer to the points. But if we increase too much, let's say we start here, we increase to here, then suddenly your cost might actually be higher than it was before. So um, one of the things in like math is that you can understand the local nature of where you are. So if I'm at 0, I can understand the local behavior of this cost function. So let's say, and that's using a tool called the derivative. So let's say I drew a line that was tangent to the curve, particularly at this point. So it's kind of like tangent, right? And at this point, what is like the slope of that tangent line? What is the slope of that tangent line? So the slope is negative. Negative something. I don't know what it is exactly, but it's a negative. And because it's negative, that tells us that if we zoom in to this right here, specifically, just this part right here, and we don't focus on anything else, if we just zoom into that particular place, if we increase the value of W a little bit, we would expect that the cost goes down a little bit, right? And that's what it means to look at the tangent line. Because although the behavior of the tangent line, if I extend this tangent line, so I'm going to zoom back out, I'm going to extend this tangent line a little bit more in both directions. As you can see, it doesn't do a very good job of replicating the cost function. But if you're near this point, it does a very good job because it's very, very close to the actual value. So we can use it to approximate what is close by to that point that we're at right now. Our initial guess being 0, since the slope is negative, and we know that a negative slope means that if we increase the value of the horizontal axis, whatever that is, in this case W, if we increase the value of W, we expect a decrease in the cost because of the negative slope. So since we want to decrease the cost, what we would do is we would take a step forward in that direction. So we would go to the right. So a negative slope means go to the right or increase the value of W. Alternatively, let's say this was our guess for W, right? Let's say this is our guess for W, right? And we want to know, should we be increasing the value of W or decreasing the value of W? Well, let's look at the slope of the tangent line at this point. The slope of the tangent line, although I didn't draw it correctly, is positive because it points upward. And that means that if we were to take a step to the right, then we expect an increase in the cost. Conversely, this actually means that if we decrease the value of W, we would expect a decrease in the cost. So what we would do in this situation is instead of going to the right, we would actually go to the left. So a positive slope means that we would go to the left. And mind you, we want to minimize the cost function, and that's why we're choosing the direction that decreases the cost function. So we would decrease the value of W if the slope is positive, but we would increase the value of W if the slope was negative. Now, let's say we have the slope. Let's say we have the slope as a numerical number, right? Then what we could do is we could just do negative of that slope, and that would represent negative of the slope, because if it's negative, then you would want to increase the value, and if it's positive, you want to decrease the value. So it's kind of like the opposite. So if I apply the negative sign to the slope, if the slope, let's say at this point was 5, right? The slope was 5, and I added a negative sign to that, then that means that I want to maybe decrease the value of my slope by 5, or decrease the value of W by 5. So W is equal to W minus 5, I guess, right? That would be your update. Or let's say in this scenario, the slope is -2, for example. So the slope is -2. If we add a negative sign in front of that, then we get +2, right? And so that basically means that we want to increase the value of W by 2. We want to increase the value of W, go to the right by 2 steps. So W is equal to W plus 2. Now, some of you might be thinking, what does W represent? W, remember, represented the slope of the slope of the line that models the data, right? And if we're increasing the value of W by 2, that might be a very drastic change. To change from 1 to, let's say, 3, to change from this to this, it's like a very drastic change. And what might happen is, in this case, let's say, instead, if you're here and you move to the right, you might be moving too much to the right and you might increase your cost too much. So what we might do is, instead of actually increasing by 2, we could increase by 2 dampened by a factor of 0.1. So instead of saying W equals W plus 2, we don't want that because that's too extreme of a change. W equals W plus 0.2, where our multiplier, let's say this is 0.1, so then this would be plus 0.2, right? It would be a smaller step size. And that actually makes sense, right? Because whatever we figured out from the tangent line was the direction in which to update, not how much to update. And therefore, if we take a small step in the right direction, then we would achieve what we want to achieve, right? Which is decreasing the cost. If we take too large of a step, we might actually undo what we're trying to do. And so this value of 0.1 in deep learning is called learning rate. The learning rate of our learning process, right? And so often it's like referred to as the Greek letter alpha. So this alpha would be your learning rate. And so W would be equal to W minus alpha times the slope, where the minus sign comes from before we were adding the negative, right, to oppose the direction, remember? Because we're trying to decrease the cost, so we take the negative of the slope of the cost function. So that's essentially how we would update it. But in the next video, I want to talk about how exactly we would get the slope of the line in the first place.